In this lecture, we are going to first discuss the push forward of vectors from one manifold to another. So, let's say you have a manifold like this. Let's call this manifold M, and you have another manifold called N. And for the time being, let us assume that both of them has the same dimension. That means if this is R of N, this is also R of N. Okay, so now what you can do is that you can equip these manifolds, both of them, with some coordinate system. So let's say we have the Cartesian coordinate system on the manifold M, and we have some other coordinate system denoted with U and V on manifold N. And there is some function that takes these x and y's to this U and V. Okay, so what happens is that points on manifold M gets mapped to points on the manifold N. So let's say you have some point over here that is denoted by x1, y1. It gets mapped to some point on manifold N as u1, v1, like this. Now, this seems pretty simple. That is just a mapping between two manifolds. But what we want to do is that we want to see what happens when I change my points from x1, y1 to some other value, let's say x1 plus a, y1 plus b. And this can be thought of as a fact that you are moving along a vector that is given by v, which has two components, a and b, like this. Okay, so how does that change on the picture that we have over N? So this is where the concept of the push forward will come. So now let's define the definition of this push forward of vectors formally. So let's say we have some function. So let's say we have some function that takes points from the xy manifold, which is a two-dimensional manifold, to some other manifold, which is also a two-dimensional manifold, and each point gets mapped with this function. Then, because of this mapping, we have induced, or we can get an induced mapping on the tangent bundle as well. And it will be clear in a moment why we are getting an induced mapping on the tangent bundle. So tangent bundle as well, and this is given by, let's say, T of P. We are considering that point from T of P to R of xy, which is a two-dimensional thing, to T of P. Sorry, this shouldn't be T of P, it should be T of F of P, because all the points are getting mapped under the function uv squared, like this, where the vectors at some point on the manifold M is getting mapped with the following: Tp of F dot Vp. And this is actually the push forward mapping, which is a induced mapping that we initially defined. It's coming from the induced mapping itself. So how does this come? Well, think of this as the following. On manifold M, at point P, which is given by this x and y's, you can think of there is a tangent space, right? And on that tangent space you can have some vector. So what will happen in this push forward mapping is that this vector will get mapped into another vector into this point, which is denoted by f of p, like this. So this is the mapped vector, or so to say the pushed forward vector. And if you want to determine how a vector like v gets mapped into a push forward vector, first we have to consider how this function itself is taking the points from M and mapping it to N. So now first we want to consider that, let's say there is some vector v of a with components a and b, and let's say our function is such that where u is equals to x plus y and v is equals to x minus y, right? So what it does is it takes some point on the xy's, x and y manifold, or the manifold M, and it maps those x and y's into x plus y and x minus y respectively. So when we take manifold M and we go from x comma y to a point, let's say x plus a, x plus b, how do we do that? Well, we can think of it as a directional derivative, this change. Why? Because when you have these 2 points, you can have a tangent space at any of those points, x plus y, sorry, just x, y, and you can think of a vector v which is given by a and b, and you can move along that vector on manifold M, and you want to see what is the consequence when we consider the mapping from M to N, right? So that's why we can think of it as a directional derivative. So since we already know that the directional derivative, let's say call it d of f, capital D of f, along the vector v is given by this guy, like this, and note the fact that it happens for both the x plus y mapping, which let's say you can denote with f of 1, and x minus y as f2. So you have to consider the changes that is coming from f1 and f2. So let's call this f1, and let's call the other one as f2. And you can write this whole thing in a compact form like this, because this f1 and f2, they are acting like the components of the total mapping f, right? And we want to find out how f itself is changing, so that's why we have to consider how f1 and f2 is changing. So if you encode them together, this will look something like this. AP, which is nothing but v, the vector, and from there you can see that this is just the Jacobian matrix or the Jacobian matrix. So you can say that the change of the mapping itself is given by the Jacobian matrix. 2 y, and there is still f2. There should be 2. Sorry, it should be x. Yes, not y. Like this one. So in a sense, the Jacobian matrix encodes the information about how the mapping F contains information about the changes in the tangent space or tangent bundle, if you want to consider every point, right? So this will also be denoted as sometimes called a T of F. This, in fact, this will be the notation that we will be carrying throughout the lectures. And now you can take any arbitrary vector on manifold M. So let's say you take any arbitrary vector on manifold M. Let's call that vector v1 as, let's say, some, what should I call it, a1 b1. Then the pushed forward vector on manifold N will be given by T of F multiplied with the vector itself. That means that you can find out the new vector, let's call that w1, if you just multiply this. And obviously this vector v1 will be at a point P. However, this w vector will be at a point f of P. And now we will see a very simple example, and we will consider this mapping that we talked about earlier. We just introduced it, but we kind of went ahead with the more general notation. So if you consider this mapping, then you can easily find out that the Jacobian is nothing but the following. So your Jacobian matrix, or T of F, is just 1. This will also be 1, this will be a 1, and this will be a minus 1. And let's consider any vector. Let's say v1 is given by, let's say, 1 3, like this. So w1 will be just, obviously you can take the base points to be 0 0, okay, or you can take the base point to be whatever you want. Let's say the base point, this vector 1 3, is defined on a point 1 1, like this. And w1 will be a vector which is given by 1 1 1 minus 1, and then you will have this 1 3. However, this whole thing will be at a point of what? 1 plus 1 and 1 minus 1, because the points get mapped by the function itself, which is given by x plus y comma x minus y, right? The u coordinate will be 2 and the v coordinate will be 0. So this is just, what is this, 1 times 1, 1 times 3, so this is a 4, and this is 1 minus 3, that is minus 2, and this is situated at the point 2 comma 0. So the vector 1 3 at point 1 1 of M, that is the manifold M, gets mapped to a vector for minus 2 at point 2 comma 0 in the manifold N. So you might ask that why we are bothering with this push forward thing. The idea is that when you talk about coordinate changes, what you are doing essentially is that you are going from one manifold to another. And the reason we are considering the push forward of vectors, because when we try to define areas or volumes, we have to deal with these vectors, right? And that's why we need to see how these vectors get mapped from one manifold to another, because the vectors themselves, they don't live on the manifold, they live on the tangent spaces, and that's why we are interested to see how this tangent space mapping is working. And when you consider all the points, then it becomes a mapping on the tangent bundle. So that's why we have to formally define this push forward of vectors. And if you consider the area spanned on the manifold, so we are again dealing with the same kind of coordinate changes as this example. So if you consider an area form like this, you will see that if you want to know how this area form changes when you change your coordinates from xy to uv, you will need to consider this push forward of vectors. Okay, so that is another reason why we are actually bothering with this stuff. And even if you do any elementary calculation, that is, you write u as x plus y and v as x minus y, and you solve for x and y, you will find that x is given by the following. It is u plus v divided by 2, and y will be given by this u minus v divided by 2, right? So dx is given by 1/2 of du plus dv, and dy is given by 1/2 of du minus dv. And then if you want to evaluate this wedge product or find the area form or the volume form, whatever you want to call it, this is just 1/4 du plus dv wedged with du minus dv. And if you do the algebra, this is 1/4 du wedge du minus du wedge dv plus dv wedge du minus dv wedge dv, and these are by definition 0. And if you flip the minus sign over here, this will become 1/2 dv wedge du, or you can equivalently write this as minus 1/2 of du wedge dv. So this is one way, an elementary way to see it, that how your area form changes. And note that this minus sign is actually telling you the orientation of the area, because if you consider this product to be a positive thing, that means this kind of orientation where you go from x to y in a counterclockwise direction, if this is positive, then when you go from du to dv in the counterclockwise direction, that will give you a negative sign. So this anti-clockwise rotation on the xy plane can be thought of as a clockwise rotation on the uv plane. Okay, so that's where this minus sign is coming from. It's because of this orientation. So this is a indicator of orientation. And now let's come back to the idea of the push forward, and we'll see that the result is the same. Okay, you see that to get any kind of area, if you think of it like this way, that you have one vector like this, let's say this is some vector, you have another vector like this, and what you can do, you can make a parallelepiped with these two vectors, right? And you can get some area. And if this is on the manifold M, so let's say this is our manifold on the background denoted with this dashed line. Since these two are vectors, we should be able to find the pushed forward versions of these vectors, and it will get mapped to this manifold. So this is M, this is N, and let's say this is the pushed forward version of this area, right? So let's say this is some A prime, this is some B prime, and we'll see that they will yield the same result. Okay, so notice that these are area forms, and what does forms do? They eat up vectors. That's what we have learned so far, that if you have any kind of form, it will just eat your vectors up. That's it, simple as that. So if we use our idea of the push forward of vectors, then we can map these vectors from A to A prime, B to B prime, and we should be able to map this area. Let's call this area as small a, and let's call this as a small a prime. We should be able to map this A to A prime, and let's see how that is done. So what we'll do, we will again write this dx wedged with dy, but note the fact that they are forms, so they should eat up some vectors, right? Vectors on the xy plane, and for simplicity we can just take the basis vectors, that means the x vector and the y vector, or the unit vectors, whatever you want to call them. So let's denote those vectors by 1 0, and this is on the point 0 0 and 0 1, like this, also at the point 0 0. And if you use the ideas that we discussed on the previous lectures, you can easily show that this is nothing but the identity matrix, which gives you a result of 1, right? And now let's consider the idea of push forwards, that is, these two vectors will get pushed forward. So the pushed forward version of this vector 1 0 will be this. 1 1 1 minus 1, there will be 1 0, and what you'll have is 1, and then you have 1, like this. Okay, so again note the fact that this is coming from the xy plane or the manifold where you are equipped with the xy coordinates and on point 0 0, and this is on the uv manifold where this 0 0 point will get mapped to 0 0, like this. Okay, and then similarly this 0 1 will get mapped as follows. So this will be 0 1, and this will get mapped as 1 minus 1. So this is on uv 0 comma 0. Okay, now what do? You simply want to find out du wedged with dv, but now these forms will eat the vectors that are the pushed forward versions of these two guys. Okay, that means this one and this one. So this is just 1 1 with 1 minus 1. Now if you compute it, what you have is some determinant given by 1 1 1 minus 1, like this, and this is just minus 2, and from here you can write minus 2 times 1, and 1 was what? Dx wedged with dy, so you can write as minus 2 times dx wedged with dy, and finally you have the relationship that we computed earlier, like this. So this very idea of push forward is actually helpful to understand how the projection of the area on the manifold M gets mapped into manifold N. Okay, and this will also enable us to discuss about pullbacks in the next lecture.